Hi, this lecture is going to cover chapter 26, the last chapter in the textbook. And we'll cover decibels, coupling circuits, filter circuits, Bode plots, and filter applications. Now, I'm going to tell you up front, a lot of these topics are just going to be very generalized. And for those of you that are electronics majors, you will go into much, much more detail on all of these topics in the Elect 53, the communications class. But we're going to introduce them here. All right, so um, with electronic circuits, a lot of times we want to tune or use our electronics to allow certain frequencies to come through or for certain frequencies to be blocked, right? And that's known as a tuned circuit. And we can do that using both capacitors, inductors, transformers, can all be used to filter. All right. And we've seen that, right? You've seen that in the labs that um, the way certain components react to certain frequency ranges will kind of give you a good idea and a prediction of what's going to happen. All right. Now, in this communication side of everything, the instead of showing the gain in um, like a percentage or anything like that, we're going to use the decibel. And the decibel is a magnitude term when signals at different frequencies at signals level occur in circuits. Now, the bell is based on the logarithm of the ratio of two voltage, two currents, or two power levels. It's named after Alexander Graham Bell, and for electronics, the bell is too large, so we're going to use the decibel or 1/10 of a bell. All right. Now decibels are based on the common log, which is base 10. You can use natural logs from which will give you base E. Now, among other things, natural logs are used to describe the exponential charge and discharge of the capacitor. Now, logarithms are used to simplify numerical computations involving exponents and powers of 10. So, like when things are really, really large or really, really small, the bell is and a logarithmic scale are used to show that. All right. So we can see that the an example of the common log are as follows. So 10 to the second power equals 100. Or you could say 10 to what power equals 100. And that's what a log is. Log 100 is basically saying 10 to what power equals 100. So log of 100 equals 2. And then log of 1,000 would be 3. Log of 17.782 would be 4.25. And then log of 0.1, which is 1/10, would be 10 to the negative 1 or negative 1. All right, so that gives you a feel of how these logarithmic values are calculated. So they're commonly used in scientific and technical calculations. Electronic calculators make it really easy to allow us to do that. Now, on the Sharp calculator, this is located under the tangent button and above the STO button. So that's the log. So let me show that here. Let me open something real quick. So I have my calculator here. All right, so on this, it's above the STO function. So it's this right here. So if I say 100 log equals, okay, that's not the right way. Let me do log 100 equals, and it tells me it's 2. Then log of 0.001 should be negative 3, right? And it is. So that's the log feature. All right. And log refers to the common log base 10, while the ln, which was also near there, right next door, is the ln, is going to be 2.783 or 718. So if I go log n at 2.718, it should be 1. Yeah, or just under it. Okay? So those are some of the calculator functionality. So then this just says, what is log of 40? You just put log 40 equals, and it's 1.6. So another way of saying this is 10 to what power equals 40? And we know 10 to the first power is 10. 10 to the second power is 100. So it's got to be between 1 and 2. And it is, right? 1.6. All right. And then the anti-log of 2.3103. So you put second function log, and it will give you the inverse log or the anti-log. And it tells us it's 200. So another way of saying this is 10 to this power, 2.3013 equals what? So you could also use your calculator and just say 10 caret 2.301303 and hit enter, and it's give you 200 as well. All right, so here's a table with some of the common logs. And we know from our algebra that if we have log of x times y, it's going to equal log x plus log y, or log x divided by y is going to be log x minus log y. So this is kind of like polar format and then rectangular. All right. Now, log of x to the y power is you take the y out front and then multiply that times log of x. And log of x of 1 over y would be 1 over y times log x. All right. Now, the decibel is the common unit of measure for power amplification, and many test equipment items are calibrated in decibels. All right. And again, like I said, you're going to really dive into this in very, very deep depth of great understanding in the Electronics 53, the communications course. All right. So there's some information about logs and decibels and all that. And I want you to read that. Go through the PowerPoint and do the calculations so you're familiar with that. And you'll get there. Now let's look at, now in chapter 25, the half power points or cutoff frequency referred to as the negative 3 dB points. This is because at the cutoff frequencies, the power output is reduced by 50% of the input power. And to find the overall gain of several stages, either multiply the power ratios together or convert them to dBs and then add them. So if we assume that an amplifier circuit has 4 stages, each of which amplifies the signal input signal by 2, what is the total gain of the circuit in dB? So we'd say dB equals 10 log of power out over power in, or 10 log of 2, which is 3. And so the total gain for 4 stages is going to be 3 times 4, or 3 plus 3 plus 3 plus 3 equals 12 dB. Alternately, we could say that, well, there's a gain of 2 in each stage. So 2 times 2 times 2 times 2 is 16. And then 10 log of 16 is also 12. So there's a couple ways you can do it. Now, in our communications, we're going to use block diagrams where you have your input and your output. So this shows the gain here is plus 10 dB. So it goes through this amplifier and it gains 10 dB. It goes through this transmission cable and it has a line loss of negative 20 dB. And then it goes up 20 dB. So if you just add this up, 10 minus 20 plus 20 equals 10. Right? And then here's a table that shows the dB gains and losses versus the power ratios. All right, so there's some equations here that you should be familiar with and be able to work on. So, but I'm gonna get up to the filter section. All right, now electrical engineers and electronics technicians use the dBm, which is the decibel ratio relative to 1 milliwatt. So this M is how much power level is there compared to 1 milliwatt. So you'll see this with dB, and have you ever seen where like a football game or a concert or something, they say we're going to set the Guinness World Record for the loudest uh, outdoor event or something. I think the Seattle Seahawks up in Seattle they set the record for that with their famous 12th man. But a typical conversation is a 60 dB. Street noise is 70. A rock band is 110. Your ears will begin to feel pain if the sound is greater than 140 dB. So it's just a reference there. Now, when we work with circuits, we can couple our circuits. So now we're going to talk about filtering and coupling. And direct coupling is one type of coupling from one circuit to another. The other type is indirect. Now, circuits that deploy direct coupling have the current of the input circuit flowing through a common impedance. So remember, impedance is Z, and then resistance is R, and then the reactance is the imaginary, or J. All right, so a voltage drop occurs across the common impedance, which represents the output voltage of the circuit. So let me see something here. All right, so the way that's working here is the direct coupling is characterized by wideband frequency responses. So we can have just a resistive circuit, which will have a power loss there, right? Because we will drop power in the form of heat across this resistor. We can have it with an inductive coupled circuit or a capacitive inductive circuit, or capacitive coupled. Now, for resistive coupling, the output voltage does not vary with the change in frequency, right? It just like in DC, it's not doesn't respond. Resistance is resistance. But for inductive, there is an increase in output voltage as the frequency increases, and then for capacitive, there's a decrease in output voltage as the frequency increases. So remember, at high frequencies, an inductor looks like an open, and then at high frequencies, a capacitor looks like a short. So these circuits are going to respond differently. So in situations where only the alternating current must be passed, then we're going to have to use indirect coupling as necessary. All right? So the capacitor will not pass DC, but will pass AC. So if the reactance of the coupling capacitor is small, say 0.1 times the resistance, with respect to the lowest frequency, compare with the resistance, practically all the AC signal appears across the resistance, and then the phase shift is kept small because the majority of the impedance is from the resistor, if the capacitor is 1/10 or less of the resistance. All right. Now, the disadvantage of this is the difficulty in making good impedance match between circuits, and this can hinder power transfer. So besides the DC component, low frequency signals will also be blocked by the capacitor. So here is a indirect coupled RC network, right, where we're taking our output across the resistor, and then the capacitor here is going to have a frequency response. So transformer coupling is considered to be another form of indirect coupling because there's no physical connection between the input and the output. So remember, in a transformer, you have the ratio of the voltage and the current is changed, and it induces the current or the voltage across the other side of this coil. All right. Now, transformer coupling is popular in radio frequency circuits, AM and FM radio, because it provides good impedance matching and allows for fine tuning. Now, fixed capacitor is placed across the transformer coils to provide a mechanism for tuning the frequency response to the circuit. Right now, filters are what we're going to call these circuits that are used in the coupling. So, and filters can be either passive or active. Passive filters use resistors, capacitors, or inductors and do not contain amplifying devices to increase signal strength. So in a passive filter, the power out is always going to be less than or equal to, it could be equal to the power in. And passive filters have no output level that is always less than the input. So the output is always going to be less than the input. Now, the reason for this is that the passive filters attenuate the input signal due to the fact that they are inserted in the line between the input and the output. And this is going to cause a loss. All right? Now, the four types of filters that we're going to look at, and then there is a section on the final exam that will ask you to calculate some of this, is a low pass filter, a high pass filter, a band pass filter, and the band stop or notch filter. So with a low pass filter, it allows the circuit that has a constant output from 0 hertz up to a cutoff or critical frequency. So it's going to allow frequencies to pass at the low end, and then when it gets to the cutoff frequency, which is his critical frequency or cutoff frequency is FC, anything after that, the signal will get attenuated or dropped. Now, frequency below FC are passed. Anything above FC is going to start to be blocked. Okay? So low pass filters can be designed using a combination of resistors, inductors, and capacitors. So here's a low pass RC filter. So it goes resistor, and then you take the output across the capacitor. And at a certain frequency range, this capacitor will then start to attenuate or block the output. Okay? And then with an inductor, you start with the inductor and then you take the output across the resistor. So this, you can do a low pass with an RC or an LR. And I'm saying that in purpose where the C is the output and then here the R is the output. Now, in the RC circuit, the output is taken across the capacitor, and that X of C is larger than R for low frequencies. Thus, most of the input signal is dropped across the capacitor. And the cutoff frequency occurs when the capacitive reactance equals the resistance. So at this frequency, the V out equals 0.0707 of Vn, and P out equals 1/2 the power. And this cutoff frequency is also known as the half point or the -3 dB power level. And if we were to graph this on a logarithmic scale, right? So this is like log -2, -1, 1, 2, 3, right? The logs there. At the 3 dB is where the circuit, -3 dB is where the circuit starts to, here it allows all of it and then it starts to attenuate it, right? So the cutoff frequency for can be found when X of C or X of L equals R. And remember, FC, which would be the frequency here, so X of C equals 1/2 pi RC, or the frequency. Now we're going to say F of C equals 1/2 pi RC, and then the cutoff frequency for an inductor is R/2 pi L, right? So if we said, what is the cutoff frequency of a low pass filter when R equals 2.2 kilo ohms and the capacitor equals 0.01 microfarads, we'd say F of C equals 1/2 pi RC and do the math, and it's 7.23 kilohertz. So any frequency, when the input on this circuit here, when the frequency gets above 7.23K, then we're going to start to see this drop here. So it'll pass all of it, and then it gets to anything low frequency it will do, and then it'll start blocking it. Okay? So there's that, and then here's with RL. So the cutoff frequency goes R divided by 2 pi L. So with that inductor, when the resistance is 33 kilo ohms and the inductor is 100 millihenry, then it's going to be at 52.5 kilohertz. Now, the RC low-pass filter is sometimes referred to as a lag network because the output voltage lags the input voltage by a specified angle. And the phase shift between the output voltage and the input voltage at the cutoff frequency or at negative 3 dB is 45 degrees. And that's because the real part equals the imaginary part. So that'd be like 5 plus 5j, they equal, so the A theta is going to be the tangent of 5 over 5, right, which is 45 degrees. So for very low frequency, x of c is large, theta is nearly 0, and the V out will equal the V in. And then for any phase shift, theta is found by taking negative 90 plus the inverse tangent of the x of c divided by r. So find theta for an RC filter at the cutoff frequency when r equals 1 kilo ohm and x of c equals 1 kilo ohm. So because they're equal, right away you know it's 45 degrees or negative 45 degrees because this is a capacitor, right? And x of c is negative 90. All right? So the output voltage of an RC low-pass filter may be found by using the voltage divider rule between x of c and r and the input voltage. So this is just doing the x of c divided by x of c squared plus x r squared, square rooted, and divided times the voltage in, you get the voltage out. So what's the output voltage of an RC low-pass filter at the cutoff frequency when the input voltage is 10 volts, the capacitive reactance is 1 kilo ohm, and the resistance is 1 kilo ohm. That's going to be the x of c divided by the square root of x of c squared plus r squared times Vn, and it comes out to 7.07 volts. All right. Now, a high-pass filter allows frequencies above the cutoff frequency, but attenuates low frequency. So it's just the opposite of a low pass. So as you can imagine, the design is just the opposite. So here's an RC high pass. So remember the low pass was R first and then C. This, even though they call it an RC high pass, just think that in a high pass, the capacitor comes first and then the resistor. And then the opposite is here. Instead of an LR for low pass, it's RL for the high pass. And the Bode plot, or the graph between the logarithmic frequency and the decibel gain or loss, it is at negative 3 dB, it starts to pass the frequency. And the phase angle for this is found the same way with the inverse tangent of x of c over r. Now the other theta, remember, was negative 90 degrees plus the tangent of that. Here it's just going to be the tangent of that, of the angle. Okay? So, and then the output voltage is calculated the same way. So you can do some of these calculations. Now, a third type of filter is a bandpass filter, which blocks is a high pass filter, then it allows it, and then it is a low pass filter, right? So this is the high pass and then a low pass. If you put those together, you get a band pass. So it can be made by combining a low pass filter and a high pass filter or employ resonant circuits. And the bandpass filter have a frequency response dictated by the application. So the half power point for the cutoff frequency on the low side becomes a lower frequency limit called F1, and then the low side is a high pass filter response. The half power point on the high side becomes an upper frequency called F2, and the high side is a low pass filter. So it starts high pass and then low pass, and then the center between F1 and F2 is known as the bandwidth. Okay, so in a resonant band pass filter, the Q factor shapes the response curve. All right, so there's that. So on, and then there's some more information on here, but on the final exam, there's just a section that will show you a filter, and it asks you identify it. Is it a high pass, low pass, band pass, or band stop? So the band stop is just the opposite of the band pass. So at the frequencies between the low pass and the high pass is everything is blocked. So it stops it. So it will allow these frequencies up until F1, and then it block it all, and then anything after F2 it'll again allow it. So here's a good picture that shows you what the low pass filter output looks like, what the high pass filter's output looks like, what the band pass filters look like, and what the band stop or a notch response is. All right? And then the Bode plot is where all of this is done on semi-log graph paper. And it just shows the how you can see that. And as we've seen, these outputs are always on a Bode plot, okay? And the linear scale is in decibels, and then the log axis is labeled in units of frequency. All right, so here's the cutoff frequency, -3, and then the decay or the slope will be at -20 decibels. All right, and you're going to do a ton of this in the communications class. I mean, really, that class is really how do you understand all this? Okay, so that's pretty much it for this chapter. And where do you see some of these filters? Well, definitely in our stereo systems, in our amplifier systems. So like when you get into Elect 51, the devices class, you'll look at these circuits with transistors, and a transistor just has a gain. So it's used in our amplifiers, and then you'll get the output there. All right, so that's it for this recording, and I will see you online.